Oh, yes, it works.
Mm-hmm.
Perfect. Okay. Also organizing this seminar. And of course, I'd like to thank my co-author, Professor Ikromov, for this joint collaboration and for inviting me to give this, for asking me to give this talk in this seminar. So it's a pleasure to be here, at least virtually. I'd like to come to Uzbekistan in person at some point, if that's possible. All right, so I don't know how many of you have heard the talk of Professor Ikromov. I understand that he has already talked about the first part of our paper. I'm going to repeat some basic results just for people who are not too familiar with oscillatory integrals. I mean, if you're an expert, then this part is probably very boring for you, but I try to give a gentle introduction so that everybody can follow the rest of the talk. And so after this brief introduction, I will then discuss the main results of our paper with Israel Ikromov, the time decay for the discrete Klein-Gordon equation. So Kg is Klein-Gordon. This will be the main part of my talk. And then at the end, I will present some additional related results with co-author from Germany, Robert Schiller, okay, which is about not the Klein-Gordon, but the Schrödinger equation in R3, so on the cubic lattice. Okay, so that will be the end. We'll discuss this at the end. All right, so to begin with, let me start with a very elementary introduction to oscillatory integrals. So what we're interested in are these kind of integrals. So they depend on a large parameter lambda and on some, we have some phase function phi. Let me see, maybe I can use the pen here. That would be good. So we have a phase function phi and we have an amplitude psi. And so the phase function is smooth and real valued, and the amplitude is smooth and compactly supported. And we are interested in estimating this integral. So the naive estimate would just be to take absolute value inside, and then this exponential factor would be killed, and we would just get a constant. But that's a very bad estimate. We want to do much better. So we are interested in estimates of this form that gain a power of lambda in its decay. So we are interested in finding the largest possible exponent R here. Okay, so all these estimates are interesting in the limit when lambda tends to infinity. All right, and the simplest result in this business is it's called the principle of non-stationary phase, which just means that, so if the phase function has no stationary points on the support of this amplitude function here, which means that the gradient of phi is never zero on the support of psi, then for any n, we have rapid decay. So I lambda decays faster than any polynomial, right? Some constant depending on this n here. And the proof is just one line, just integrate by parts n times. And each time you integrate by parts, you gain this factor of 1 over lambda. Okay, that's when you are non-stationary. And then, of course, the interesting phenomenon happens at stationary points. So we say a point x naught is a non-degenerate stationary point. If, well, first of all, it's a stationary point, which means the gradient at this point vanishes. And non-degenerate means that the Hessian at this point has non-zero determinant. So the Hessian has maximal rank, namely D. Okay, D is the dimension of the space here. And so the stationary phase lemma or proposition here says that in this case, we have decay of lambda to the negative of the half of the dimension. Okay, and the proof is also not difficult. So you can always localize. You can assume that your amplitude function is supported in a small neighborhood of the origin here, and then you just decompose your integral into two pieces, a local piece and a global piece. So here this rho is just a compactly supported function. So this is the I1 is the local piece, and for this you just use a pure size estimate. So what you do is you just estimate this by killing this and taking absolute value inside, and you get this desired decay, and then you treat the global part I2 by a non-stationary phase, because now you have localized away from the critical point. You can use the non-stationary phase estimate, and then so if you don't know what to do, then you just put lambda to some arbitrary power here, and then at the end you optimize it, and you find that lambda to the 1/2 is the optimal power that you should put in here. Okay, so that's
non-degenerate case. You can change phi by x squared. Yeah, that's enough.
Yes. That's another proof. You can use the Morse lemma.
Yeah, Morse lemma.
Yes. You can just use. Yes, of course. That's also true. Right, and so what we're interested here when we're discussing PDEs are actually stationary phase with parameters. So when we talk about PDEs, we will always have parameters in these oscillatory integrals. So the parameter here is denoted by x, which means that both the phase function as well as the amplitude function depend on additional parameters. And we want to have estimates that are uniform in the parameters. Okay, so if we assume that the amplitude function has symbol type bounds like so, and has support in a sufficiently small neighborhood of the origin, again, this is no loss of generality, then the generalization of this stationary phase lemma with parameters is this result here. So again, we get a decay of lambda to the minus d/2, and we can also take derivatives of this expression. So the thing that we have to do is we just have to multiply I by this phase here, and then we get the same estimate as without parameters. Okay, and again, you can prove this by the Morse lemma, by using the Morse lemma. This time use the Morse lemma with parameters. So that's one possibility to prove this. Okay, now let's talk about degenerate stationary points. So now suppose that the Hessian of phi is degenerate at a stationary point, which means that the determinant vanishes at this point. What can we say about I lambda, about this oscillatory integral? And so we consider the one-dimensional case and the higher dimensional case separately, because it turns out that the answer in one dimension is very simple. There is a satisfactory answer given by the van der Korput lemma. So this is a classical result, which says that if you have this lower bound for the kth derivative of your phase function, let's say k is at least 2. There is also a version of this for k equal 1, but let's not bother with this now. Then the oscillatory integral is estimated by lambda to the power minus 1/k, and you have explicit control of the constant. So this is given by an explicit, so just a k-dependent constant times something which depends explicitly on the amplitude function. And unfortunately, in higher dimensions, we don't have a good analog of this van der Korput lemma. We only have very weak analogs of this lemma. For example, if you look in Stein's book on harmonic analysis, you find a version like this. So if your phase function has some partial derivatives some partial derivative of order k here is bounded from below. Rarely optimal, as you can see from this simple example. Just take a phase function in 2 dimensions, the product of the 2 coordinates x1, x2, and so of course the derivative dx1, dx2 of this is equal to 1, so you get k equal to 2 here. But actually the stationary phase lemma tells you that you should get k equal to 1, right? Because this is a non-degenerate phase function. The Hessian of this has non-zero determinant. So this is not optimal in general. And okay, why is there such a discrepancy between 1 dimension and higher dimensions? Well, the reason is that in 1 dimension, you can always write your function in a normal form. You can choose local coordinates, say at the origin, such that your phase function is plus or minus x to the power k. And there is no analog in general for higher dimensions except for k equal to 2, and then you have the Morse lemma, which I already mentioned. So the Morse lemma, of course, says that, right? So if you know that the Hessian is non-degenerate, then you can find local coordinates such that phi is a pure quadratic form, right? You have so there should be a plus here as well. So with signature j in this case, right? J of these squares are positive and the other ones are negative. But this is special for k equal to 2. Okay, so let's talk a little bit more about the phase function and about singularities of the phase function. So what do we mean by a singularity of the phase function? So we say that a critical point x naught of phi is a singularity if the rank of the Hessian is less than d. And so let's call this rank r. And then the co-rank of the singularity, or sometimes called the number of active variables, is just the difference, the difference of d and r. And by standard lemma I'm not really sure to which field this lemma belongs, but it's called the splitting lemma. You can always find local coordinates such that your phase function can be written just as the sum of a function depending on the active variables plus the quadratic form in the remaining variables. Okay, and so if you are interested in oscillatory integrals, once you have this this splitting, and then you take e to the I lambda phi, this will be e to the I lambda f, e to the I lambda q, of course, and then you can just integrate out the variables xr plus 1 up to xt by using stationary phase. And each time you do this, you gain a factor of lambda to the minus a half. Okay, so really the only thing to worry about is are these active variables. So that's why they're called active. And right, so there are normal forms of these functions that can appear, and they are tabulated, for example, in the books of Arnold and I have it here in my bookshelf, but I can't see the other authors. Pardon me, you probably know the names better than I do. Right, so these singularities are tabulated, so there are certain normal forms, and if you can find the normal form, then you basically know how fast your oscillatory integral will decay. Okay, so there's a classification of singularities. Let's look at the simplest singularities, and these are called co-rank 1 singularities. So if r is equal to 1, right, this is the condition here, the rank is equal to d minus 1, and in addition we assume that so the gradient of this determinant is non-zero, right? So this is sort of a non-degeneracy condition, and it guarantees that this set here, the set where the determinant of phi determinant of the Hessian is 0, is locally a smooth manifold, and so that and there exists a kernel vector field. This is in general non-unique, so which means that there exists a vector field V along this manifold such that V of x lies in the kernel of the Hessian of phi at x. Okay, and then we consider two situations. The first situation is when this kernel intersects the tangent space at x, the tangent space of sigma at x transversally. So we have transversal intersection, or what is the same, an analytic expression of this is the following, is that the gradient of the determinant of the Hessian dot product with V is non-zero at x naught. And then we call the singularity a fold, or a Whitney fold. And I will mention Whitney again later, or in the terminology of Arnold, it's an A2 singularity. And if this gradient dot V vanishes to first order at x naught, so if we have tangency, but only to first order, then we call the singularity a cusp, or A3 in the Arnold terminology. Okay, so these are the simplest singularities that can appear. And so, okay, what is the relation of these singularities to the oscillatory integral? Again, let's consider an oscillatory integral depending on parameters x. And then we say, so this is a definition, we call the set of those parameters x for which the oscillatory integral decays slower than what would be predicted by stationary phase, namely lambda to the minus d over 2. We call this set the caustic. Okay, and so on this caustic we have some decay like this, right? Maybe modulated by some logarithms, and then we call the singular index just as the difference between this and this, right? So d half minus sigma. So this is always positive, right? Or on the caustic, this is always positive, this sigma, this singular index. Okay, and so there are these famous 7 elementary catastrophes of Thom, and in dimensions at most. So if the dimension is at most 4, or which means this R, the co-rank of the singularity, is at most 4. I should probably write R here. The only stable okay, and there's also a mistake here. So the only stable singularities are these 7 so-called elementary catastrophes: the fold, cusp, swallowtail, butterfly, elliptic, hyperbolic, and parabolic umbilic. And then they also have these other names. So these are the A singularities here, and these are the D singularities. And it turned out in our analysis of the Klein-Gordon equation that all these singularities except this one, the D5, appear. And in addition to these stable singularities, we will encounter an unstable singularities, and it's called like this, T444. So this singularity appears in our analysis in 4 dimensions of the Klein-Gordon equation. Okay, and as I already mentioned, the knowledge of the type of singularity allows you to determine the singular index. So if you know you have an A2 singularity, you know your oscillatory integral decays in a certain way, for example. And in fact, the AK and DK singularities, so this singular index has been found by Deustermatt for these kind of singularities, and for the unstable singularity that we have in 4 dimensions, there is a result of Karpushkin from the 80s that gives us the singular index. And also Israel has an alternative proof of this result, which is more robust, which is sort of doesn't use resolution of singularities or things like that, but it uses dyadic decompositions. I don't know if he has talked in your seminar about this, but he has given a presentation in our seminar 2 weeks ago, and so he had a very nice proof of this difficult result of Karpushkin. So this is the most difficult case that comes up in our analysis, and Israel has found a nice proof of this. Okay, so here is a table listing the singularities that appear in the Klein-Gordon equation. So as I just said, we have AK singularities for K 1, 2, 3. We have DK singularities for so D4 plus and D4 minus, and we have this this unstable singularity here. And here in the second column, I've noted the normal forms. So I just show you the active variables. So for AK singularities, there is just one active variables. For DK singularities, there are 2 active variables. And for this unstable singularity, there are 3 active variables, x1, x2, x3. And in the last column, I show you the singular index, so the difference between d over 2 and sigma. So let me recall that sigma is the exponent, is the decay exponent. Okay, so this is you can just read it off. If once you find the normal form here, you can take this k and plug it in here, and you find your decay index or your singular index. All right, so the main problem is given an explicit phase function and an explicit amplitude, but the amplitude is not so important. Find all the all the singularity types that can appear in this problem. Okay, so now let's go to the discrete Klein-Gordon equation. So right, so we look at we consider the Cauchy problem of the discrete Klein-Gordon equation. So this is the initial value problem. So we have an initial initial amplitude at time 0 called f of x, and an initial time derivative of this initial amplitude at 0 is called g of x. And then we look at this equation here. So this is the Klein-Gordon operator here, 1 minus the Laplacian, and the Laplacian is the discrete Laplacian. So it's the Laplacian on the lattice. Right, so it's delta x applied to psi. Okay, I should use this.
Klein-Gordon equation, discrete.
It's discrete, yes. So delta x applied to u of x is the sum. So it's this operator, the discrete Laplacian. Okay. All right. Oh, actually, there.
Mine's there is a necessary to add the weight in the center. Yeah.
Yeah.
The correct definition is over there. Yeah.
Yes, it's there.
Minus the 2d is dimension. Yeah.
Yes, I didn't see it. Of course, you can always subtract the constant from it, and we take this. We subtract this constant.
Is it discrete with step h equals to 1? Yeah.
It's h equals to 1. Yes. So it's a discrete. It's a lattice of mesh size 1.
Okay.
Discrete.
Yes. All right. And so we want to do Fourier analysis. So we want to use plane waves to analyze this operator. So let's take a plane wave like this. And we see that once we apply the operator to this plane wave, we get dispersion relation omega. omega squared in this case, but omega is given like this, right? It's the square root of this function here. And this is an easy exercise to do. You just, do it explicitly, and you find this dispersion relation. And so the thing is that this dispersion relation is quite complicated from the point of view of doing oscillatory integrals. First of all, it's not a polynomial. It's something else, and second of all, it has the square root, which makes it a bit unpleasant to work with. But so it will turn out that this thing will have singularities, and it's much more difficult than in the Schrödinger case, because in the Schrödinger case, what you get, you just get the sum of cosines, and when you do the oscillatory integral, right, you have e to the sum of cosines, and you just get a product of e to the cosine of one variable. So in the Schrödinger case, everything becomes trivial because the things factorize. So you just have to do one-dimensional oscillatory integrals. In the Klein-Gordon case, because you have this square root here, your oscillatory integral doesn't factorize. So it's a genuine higher dimensional integral. Okay, so it's much more difficult than the Schrödinger case. All right, and so let's go back to the PDE, to the Cauchy problem. So the solution of the Cauchy problem can be expressed by Duhamel's formula. So this is a well-known thing. So for sufficiently regular initial data, we can do a Fourier analysis and Fourier transform the equation. Then we just have an ODE and time. We solve the ODE and time, and we Fourier transform back, and we end up with these with this solution. Okay, so. And of course, we have Euler's formula, so we can always, we can write cosine of x as e to the ix plus e to the minus ix over 2, and similar for sine. So what we end up with is a sum of oscillatory integrals of this form. Okay. So and here the phase function will be x times psi minus t omega psi. Okay, and so so what you should think of, compared to the general theory I showed you at the beginning. So here the role of lambda is now played by t, and the role of x, of this parameter, is now played by actually, well, x, right? But
sorry, who was the first who used this representation of the solution like oscillatory integrals for the discrete Klein-Gordon equation?
Who was the first?
I think not Klein, not Gordon, yeah?
Probably not, but I don't know. I don't know the history really of this.
Okay.
Sorry. All right. So we will study this integral here. Okay, and also it's convenient to write x as velocity times t, so that we can factor out the t, because we want to. So t is now our large parameter, right? T is the analog of lambda at the beginning, right? So if we factor out the t and we write x as velocity times time, we are considering essentially integrals of this form. So e to the it times a function, phase function, which now depends on v and psi. V are the parameters, the velocities. So they are, the space of parameters is d-dimensional, right? Because we are in RD. And the phase function is just of this form. And it's easy to see that there is an alternative formula for the dispersion relation, namely this one. And using this formula, it's easy to see that the gradient of omega in absolute value, so the norm of the gradient is at most 1, right? And this is just an expression of the fact that the Klein-Gordon equation has finite speed of propagation, right? So if you take if you solve this equation here, then the solutions of this equation V, so V is equal to the gradient of omega xi, right? So V has at most norm 1, okay? So we're always inside the light cone, so to say, okay? So this is the finite speed of propagation. Outside the light cone, this integral decays faster than any polynomial, right? Then we have non-stationary phase. In fact, one can show using steepest descent that it actually decays exponentially, but that we will not talk about this. But so we're interested in the decay inside the light cone. Here we have to analyze the phase function more carefully. Okay. So here are the main results of our joint work with Professor Kromov. So we did this in dimensions 2, 3, and 4. Okay, and then we have some conjecture in dimension 5 as well. And so all these decay estimates are sharp. So these exponents here, -3/4, -7/6, and -3/2, and the logarithm, they are all sharp. So this is one can find a V here or an X here, such that at the point X, this is the exact decay of the integral. All right, and so this theorem answers a question or a conjecture of Kefrakidis and Stefanov in a paper published in the same journal. So this is published in Nonlinearity this year. And some years ago, Kefrakidis and Stefanov, they conjectured that one should have the decay I t x less or equal than constant times t to the minus d/3. Okay, because for the Schrödinger equation this is true, but as I already told you, the Schrödinger equation is much easier because the oscillatory integrals just factor into a product of one-dimensional integrals, and then you just have to prove this for dimension equal to 1, and then you can use the van der Korput lemma. So they proved this for the Schrödinger equation, and they conjectured that the same should be true for the Klein-Gordon equation. But if you look at our results, so let's take d equal to 2, for example, then you have 2/3 here, but we actually have we have 3/4. And also if you take d equal to 3, you get t to the -1, but we get t to the -7/6, which is better. And the same in 4 dimensions. So in 4 dimensions, you would have t to the -4/3 in the conjecture, but we have t to the -3/2 up to a logarithm. So we showed that actually, I mean, the conjecture is true, but actually one can prove better estimates. So the estimates for the Klein-Gordon equation are better than the estimates for the Schrödinger equation.
The power of logarithm in this conjecture, the d-4, it looks like maybe d-3, it's not correct, yeah?
Oh, yes, that's true, yes. Thank you. So, yes.
Maybe.
Yeah.
Okay.
It would be consistent with what we have here.
Yeah,
yes.
yeah.
You're right, yes. Thank you very much. Okay, yeah, so we did this analysis in dimension 2, 3, and 4, and each time you increase the dimension, you increase the number of cases that you need to analyze. So the number of singularities of the phase function grows with the dimension. So this is not an easy thing to, I mean, it's not straightforward to generalize this to higher dimensions. So we conjecture that there is an estimate in higher dimensions, but we haven't proved it yet. And also let me say that actually the two-dimensional case was already known before our work by these two authors here, but they apparently didn't know about this conjecture. So they didn't mention the paper of Kefrakidis and Stefanov. They had sort of different applications in mind, but they proved this in 2D. And then there is a related result by Schultz in 2 and 3 dimensions, but this is not for the Klein-Gordon equation, it's for the wave equation. So the wave equation, if you let me go back here to so the wave equation would be when you just have this operator here without the 1. Okay. Right, but this case here, 4 dimensions, this is completely new, and also it's the most difficult case in our paper. So this is where this non-stable singularity, this T4 singularity pops up. It pops up in 4 dimensions. All right, and okay, now let me discuss some PDE applications as promised. But I have to say that actually the PDE applications are quite standard. So once you have the decay estimates, there are many sort of standard machineries that you can use to get mixed norm space-time estimates, like for example Strickard's estimates. So really the decay estimates are the key thing. They're the hard estimates that you need to prove, and then once you have them, you get a lot of other estimates for free. So here are the Strickard's estimates, and I mean I don't want to read all these exponents here. This is just what comes out of the general machinery. What was there a question?
Sorry, just a mistake of one participant.
Okay.
No problems.
All right. So right. So instead of explaining the numbers here, let me explain the general machinery that is used to convert decay estimates to Strickard's estimates, and this is due to many people, but sort of the definite result is due to Kiel and Tao from the 90s. So remember that we had a decay estimate like this. So we have some decay of the oscillatory integral, time decay t to the power minus sigma, and then we say that 2 exponents or a pair of exponents q and r, so these are numbers between 1 and infinity, are sigma admissible, right? If these conditions here hold, so sigma enters here, right, in this inequality here, and there is also a notion of sharp sigma admissible when you would have equality here, okay? And so basically, so many of these cases were already known before the work of Kiel and Tao, but Kiel and Tao proved an endpoint case. So the endpoint where right, so when we have equality here. Okay. All right, so this is the theorem. This is just an abstract result. So assume you have an operator ut from some Hilbert space H to some L2 space. And of course, in our case, ut will be the propagator. So it will be e to the t square root of 1 minus delta, or this, right? So the time evolution operator. And then assume that you have an energy estimate, which you always have for this kind of operator that I just wrote down. So this estimate here is always trivial, and most of the time this is trivial in PDE applications to prove. And then assume also that you have this time decay estimate, and this is the hard estimate. This is the thing.
What is the meaning of the S here?
What is meaning of S?
S. T is understandable. S.
Yes, and actually, there's a misprint here. Yes, this should be S here. I mean,
okay.
T and S are both. They're just times. They're just times.
Yeah, now it's understandable.
Now it's clear. Okay, thank you. Right, and actually, in our case, where is the yes? So in our case, U of T, U of S star will just be U of T minus S. So we have a translation invariant thing, right? Because our Hamiltonian is independent of time, the Klein-Gordon operator. But in any case, this is just a general theorem. So then once you have these two estimates, you can combine them and you get all these Strickhart's estimates. So the first estimate and the second estimate are equivalent. They are equivalent by duality. And the third estimate is sort of a truncated version of the second estimate, where you restrict to the causal region where S is less than T. Okay. All right. So this is the abstract theorem, and if you plug in our estimates, our time decay estimates into this theorem, you combine them with. Oops. What happened?
There is a more general theorem of tau. Yeah, you just can apply it to Klein-Gordon equation.
Of course, it's more general. Yes.
More general than Klein-Gordon. Yeah.
It's more general than Klein-Gordon.
Yeah. Sure. Yeah, I see.
Do you still see me? There is sort of a problem here. Do you hear me fine?
Yeah.
Okay. Sorry, but I had a problem on my computer. All right. So yes, exactly. You take our time decay estimates here, you plug them into this kill-tau machinery, and you get these Strickhart's estimates. And these are the exponents that come out. Okay.
Sorry, with this P and Q with a line or this letter.
These are just, yes. So these are just different. I mean, this is a pair of admissible exponents, and this is another pair of admissible exponents.
Yeah.
So you can choose Q, R, and Q bar, R bar independently. They have nothing to do with each other.
No connection between them.
No connection between them. No. So I just noticed I should have written, of course, what they have to satisfy. But let me go back here. So Q and R, they should both be sigma admissible, right? QR should be sigma admissible, and also Q bar, R bar.
They must be sigma admissible.
Exactly.
Okay.
Independently.
Okay.
Independently. Yes, exactly. Thank you very much. All right. Okay, and let's discuss another application, or actually a consequence of these Strickhart's estimates. And so the usual thing, so what people use Strickhart's estimates for is in PDE is to prove well-postedness of nonlinear PDE. So far we have discussed the linear Klein-Gordon equation, but now let's look at the nonlinear Klein-Gordon equation. Okay, discrete nonlinear Klein-Gordon equation. So this is this equation here. So the nonlinearity is a power nonlinearity, u to the 2s times u. And so we assume that the nonlinearity satisfies these conditions here, depending on the dimension. And this is, I mean, this just...
It looks like just the same numbers as in your theorem, yeah?
Yes, these are exactly the same numbers, yes. These are the same...
Except logarithm.
Exactly. So that's why there is a strict inequality.
Strictly, because there is a logarithm.
Exactly.
Yeah.
Yes, because of the logarithm.
Only because of logarithm. Yeah, okay.
Yes. All right. So a standard result that you can prove once you have Strickhart's estimate is the following. So you can prove small data global well-posedness, which means that if you know that your initial data are small in say in the energy norm here, then the equation has a unique global solution, and this solution is bounded in the Strickard's norm by constant times epsilon for any Strickard's pair QR. So for any sigma admissible pair that we defined on the previous slide, and this. So this is a standard result, and the proof is a contraction mapping argument. So you construct a metric space for which you're, if you write this equation in its weak form, so you do the Duhamel form, you write this as an integral equation, and then you can understand it as a fixed point equation. And then
some kind of fixed point theorem, yeah?
Yes, it's a fixed point theorem, exactly. And for the fixed point theorem, you need the Strickard's estimates, because even though you're assuming that your initial data are in L2, the nonlinearity will take them out of L2.
And because of that, you need this norm of L infinity with respect to T.
Exactly, yes. Yeah. For this reason, we need the mixed, these mixed.
Uniform norm.
Exactly, yes. Yeah. That's correct.
Because of that, you can prove the global solution, the existence of global solution. Yeah.
Yes, exactly. Yes.
It's understandable that if epsilon is a little bit bigger, maybe there is no solution at all. Yeah. This is possible, I think, to show the counterexample.
You mean that large data global well-posedness fails?
Maybe it cannot go too far with respect to T.
It is possible, yes. I haven't thought about this. I mean, usually large data global well-posedness is much more difficult to prove than small data, because you need to exploit certain conservation laws. You know, for example, you use that the energy and the L2 mass is positive, things like this. But for the discrete Klein-Gordon equation, I'm not aware of any results about large data global well-posedness. But I will keep this in mind. This is a good question.
It seems that for big S, yeah, you cannot prove the existence of the global solution.
This is possible, yes, it's possible. Mm-hmm.
Okay.
Thank you for the comment. Yes, so the last part of my talk, now I come to something different and something easier, actually. So we will leave the Klein-Gordon equation, and we will, in a moment, we will consider the discrete Schrödinger equation in R3. And before I go to the Schrödinger equation, I want to discuss a little bit surfaces in R3. So, okay, consider a surface in R3, compact, smooth, and we are interested in the decay of the Fourier transform of the surface measure. So now I didn't write what this is, so maybe let me.
Not necessarily convex.
Not necessarily convex, right? Yes. So mu hat of x is the integral over the surface e to the minus I x psi d sigma psi. Right? So that's the thing that we consider here, Fourier transform of the surface measure. Yeah, I should maybe write the mu psi here. It's better. All right, and so there is a standard result that if your surface has non-vanishing Gaussian curvature, then the Fourier transform will decay like 1 over x at infinity. 1 over x.
Is it Randall or Hertz? No, Randall maybe, no?
This result?
Yeah.
Again, I think
if there is non-vanishing Gauss curvature.
If there is non-vanishing Gauss curvature, I think this is a classical result of maybe Hertz and
maybe Hertz, yeah.
Yes, I mean it's very old, certainly.
Yeah. Okay.
Yes, and also if you know that you have just one non-vanishing principal curvature, then you get half of that decay. And this presumably is due to Littmann, Walter Littmann. So this Littmann has a paper about, if you know that K, you have K non-vanishing principal curvature, then the Fourier transform of the measure decays like x to the minus k over 2. All right. And so I want to sort of explain in the following that in some sense, generically, whatever this means, we should expect that we have half of this. So we have the average of these two things, right? So we have decay x to the minus 3 over 4 generically. All right, so let me explain again what I mean by this. So I already told you about the Whitney fold and the Whitney cusp singularities at the beginning. So this is just sort of a repetition, but from a slightly different perspective. So now we are looking at surfaces in R3. So we can consider their Gauss map, right? So this is a map from a two-dimensional surface to another two-dimensional surface. And the Gauss curvature is just it's just a determinant of the differential of the Gauss map, of course. And right, so this condition here is equivalent to saying that the Gauss map is a diffeomorphism at P, or in other words, the rank of the differential is maximal. There is no singularity in the language of singularity theory. And for these generic surfaces, we allow singularities. So we consider the case where the Gauss curvature vanishes at a point, but we assume again this non-degeneracy condition that if the Gauss curvature vanishes, then its differential doesn't vanish. Okay, and so again, I already explained. Then this set is a manifold. It's because we're in R3, and we have so now we have this condition here. This will be a curve, okay, a locally smooth curve, and we choose again non-vanishing tangent vector field V to this curve, just like before. And also, like before, we say that P is a fold singularity if this the differential of the Gauss map applied to V does not vanish at P, and it's a cusp singularity if this quantity vanishes linearly at P. Okay, so this is just a repetition from what we said before. And so we call the class of surfaces that have only fold or cusp singularities or no singularities, we call this class C. Okay, and now, so this is the reason that I call this generic. This is a classical paper of Whitney. Basically, this the start of singularity theory. I mean, it started with this paper more or less. So Whitney considered maps from the plane to the plane, from R2 to R2, right? And he sort of classified the generic maps between surfaces. And so the theorem of Whitney in modern language would be like this. So let X and Y be surfaces or two manifolds. Then there is a residual set, so the complement of a countable union of nowhere dense sets in the C infinity topology, such that every map in this set has only fold or cusp singularities. Okay, and these maps, so these are maps from R2 to R2. In suitable local coordinates, they have these normal forms. So this is the fold here. So I drew a picture of the fold. So the map would be the map that sends the lower the plane in the bottom to the plane in the top, and the map for the cusp would be this map here. Okay, so these are the only so generic singularities for maps in the plane. Okay, so since the Gauss map is such a map, it's a map from a two-dimensional manifold to a two-dimensional manifold. Whitney's theorem justifies that we call this class C generic, so the class where we only have fold and cusp singularities. Okay, and this is a theorem with a co-author from Germany, from Karlsruhe, Robert Schipper. And it's not a very difficult theorem, but we thought it's worthwhile to publish it because we gave essentially a very elementary proof of this result. So we proved that if sigma is a surface, is a generic surface in this sense, then we have this uniform estimate, which is basically the average of the x to the -1 and x to the -1/2 that you would get from the cases where you have where all curvatures are non-zero or where just one curvature is non-zero. And as I said, the estimate is not new. It's essentially known by results of Karpushkin, but our proof is much simpler. It basically only uses stationary phase with parameters and the van der Karput lemma in one dimension. And for this reason, it's sort of, we thought it would be worthwhile to publish it. And let me also say that Erdős and Salmhofer a couple of years ago have actually established this result with a logarithmic loss. So not quite x to the -3/4. And also their estimate is not quite uniform in all directions. So it sort of blows up in certain directions. But this is completely uniform. And let me also say that I owe thanks to Professor Kromov for many valuable discussions that inspired the proof of this result. Actually, we started the project on the Schrödinger equation with Professor Kromov, but then another person had a preprint on the archive, which basically did exactly what we were trying to do. So we abandoned this project. We focused on the Klein-Gordon equation, and in the meantime, this co-author from Germany published a preprint which contained a mistake. And since I already had all these calculations, I contacted him, and we published this sort of short note which superseded his previous preprint. But actually, Professor Kromov helped a lot in this business as well. So, and I have to say, compared to the estimates that I discussed before, the Klein-Gordon estimates, these estimates here are very simple. So the other ones for Klein-Gordon equation, they are much more difficult.
So in this estimate of Erdős Salmhofer, there is the right-hand side is multiplied by logarithm. Is it so?
Yes, there is a logarithm, yes. But
it's worse than the result of Karpushkin. They didn't know this result of Karpushkin?
They didn't know this result, no. They did everything completely by hand. So they don't use any methods of singularity theory whatsoever. They do sort of everything with dyadic decompositions and with elementary. But they use elementary means to do this.
Yeah. Okay.
But yes, in this sense, we also in this paper here we also use very elementary means, but in a more precise way. So we use sort of baby singularity theory to do this. And so here is an application to discrete Schrödinger operators. So again, let's consider this. So here it's a slightly different convention for the Laplacian that I use here, but we are in 3 dimensions. So I have some constant minus this thing here. So this is the discrete Laplacian in 3 dimensions, and we consider the Schrödinger operator. So we add a potential, okay? And the potential will be an LQ, nothing, well, essentially an LQ. I will show this in a second. All right, so we have 2 possibilities here. Either the potential is a deterministic potential, and we assume that it's in L7/4, or the potential is a random potential. And actually, the assumption is that this randomness is either Gaussian or Bernoulli, so mean zero Gaussian or symmetric Bernoulli. And in this case, in the deterministic case, we can basically reduce the decay by half. Okay, so if you look at the exponents, here we have to assume this 7/4 integrability. Here we only have to assume this 7/2 integrability, right? So the higher the exponent here, the less decay at infinity is assumed. And also the little LP spaces, they're nested, right? So this one is always better than the other, not like capital LP. And also in the random case, we have to lose a little bit of we lose an epsilon of decay. So there is a way to get rid of this, but the simplest result uses an epsilon here. And then the statement is that the wave operators, so these objects, these are classical objects in scattering theory, they exist and are complete. And in the random case, this statement is meant almost surely. So for a set, for all omega except in an exceptional set with small measure. All right, and here is the explanation of what completeness means. If you don't already know, it just means that the range of these operators are equal to the absolutely continuous subspace of the Schrödinger operator. And so a similar theorem was proved by Korotyaev and Muller 2 years before, but they assumed this stronger condition, right? They assumed P is less than 6/5, and we assume that P can be as large as 7/4, and then the random result is even stronger than that. Okay. And to finish, I just want to show a glimpse of sort of what goes into this random result, and it's a very clever idea of Bourgain. So he used this in the context of scattering theory for the Schrödinger operator on the two-dimensional lattice, not on the three-dimensional lattice. So two-dimensional is sort of a bit easier because the surface, in this case, the dispersion surface, is curved, and in 3 dimensions, there are points where the curvature vanishes. But the strategy of Bourgain still applies. So he uses these so-called entropy bounds. Okay, so I just want to explain a little bit what this means. So consider a linear operator from a Hilbert space. So H is a finite dimensional Hilbert space to another finite dimensional space, but with non-Euclidean norm, with the L infinity norm here. And for any epsilon, let n of epsilon be the maximal number, the minimal number of balls in this space here of radius epsilon that you need to cover the image of S. So the image of the unit ball under S. Okay, and this can be estimated using an entropy bound that is due to these authors here. And Bourgain converted this bound to the following estimate. So the main thing here to observe is that n doesn't enter in this inequality, right? I said that so n is a finite number, but actually, sorry, there is a misprint here. This should be m here, right? And the Hilbert space has dimension n, whatever that is, but the point is that the dimension of the Hilbert space does not enter in this inequality. Okay, and so then one can use this for a discrete version of the Fourier extension operator, which is this operator here, and I don't have much time to explain this, so I will stop at this point, and thank you very much for your attention.
Thank you. Any questions, dear colleagues? Maybe some. Sorry, I interrupted you by a lot.
No, that's fine. It's
yeah.
Just
no questions.
Just a question.
Okay, Russia.
Professor Cuenin, can you open the estimate of oscillatory integrals?
Yes. Which one?
From very beginning, your result with Professor Cuenin.
Yes.
Oscillatory integrals in two-dimensional and three-dimensional and four-dimensional cases.
Right. I went too far. Here.
Yeah, here. Yeah, you see, as far as we know, you have some result about that these estimates cannot be improved. That means this sharp. So you cannot get better results, right?
Yes,
so,
that's true.
Yeah, because otherwise it's very difficult to understand why do you have this logarithm.
Yes.
So this is essential here.
It is, yes.
Yeah.
All three estimates can be improved, yeah? Or only the third? I remember about the third. You cannot throw the logarithm.
No, all of them cannot be improved.
Sharp.
All of them.
All of them.
All of them are sharp, yes.
It's very interesting.
And also the logarithm, you cannot get rid of the logarithm. The logarithm is sharp as well.
Yeah. More questions?
No, thank you.
I see. I can say that this presentation was excellent from my point of view. Yeah,
thank you
because
very much.
now I understand this connection of these oscillating integrals with Klein-Gordon equation. Yeah.
That's good. That was my goal, to explain this.
Yeah, and I think that there are a lot of problems concerning with these things, which can be many people continue these investigations. Yeah,
absolutely. Yes.
Yeah, and because especially in many dimensional cases, just this is your conjecture. Yeah,
this is our conjecture, yes. This conjecture here, and we would like to make progress on this. But what is also interesting is, for example, in the Schrödinger case here. So if you are considering surfaces in R4 or R5 or whatever, then this business also becomes much more complicated. So this simple result that we proved here with my colleague from Germany, this works in 3 dimensions. In higher dimensions, it becomes very difficult, and there are many interesting applications that would follow from oscillatory integrals in higher dimensions.
You didn't mention the connection with Newton polyhedron, yeah.
Yes, of course. There is a whole there is a whole business of techniques behind.
I know that some pupils of Washington, they are working in this field. Yeah.
Okay.
But I don't know exactly the last results in this field. Yeah.
Right. I mean, to be honest, I'm not. I mean, Israel is the specialist in this business. I was sort of more the person to convert these things to PDE, applications for PDEs. I have some basic understanding for these estimates, but all these, these hard estimates, these complicated singularities. So this was Israel who did this.
It looks like there is a connection with Fourier integral operators. Yeah.
I think so. Yes. Yes, probably there is. Yes. I think so.
Okay. Thank you very much. No more questions? And in this case, on behalf of all the participants, I would like to say you thank you very much for this very interesting presentation. I hope that maybe next year or maybe later you will come to Uzbekistan and we can see your report offline maybe.
With pleasure. Yes.
Yeah, it would be very interesting.
Yes.
Thank you very much again.
Thank you very much for the invitation again.
Yeah. Thank you very much for everybody. Goodbye.
All right.
Yeah.
Goodbye.
Арсен Владимирович,
Да.
как идет подготовка к...
Все нормально, все хорошо, спасибо. Мы вот в ближайшее время отправим